Hello, science class. Today we're going to be talking about chapters 1.2 and 1.3, talking about Hess's law and all the energy involved around it. So, to start with this, we're going to jump right into how do we get energy? And really, it all comes from the sun. So when we think of it, the sun is the fuel for everything. It's just been converted and released and stored in many different ways. What we see here is pictures of flames and fires and how we can see the amount of energy being released from these fires. How do we track all this energy back? Well, the stars are an energy source, so our sun specifically gives all this energy to allow these trees to grow. And hopefully remember how that happens. So we just finished talking about nuclear fission reactions and fusion reactions. And so what the sun is a giant fusion reaction. The sun's core produces energy that is emitted into space as EMR, and we see it as the light hits our Earth and it just allows us to see everything. But we know there's more to EMR than just the visible light. There's also thermal energy, so the infrared levels, and we can actually feel that warmth of the sun. And this helps drive our water cycle and helps drive our weather. And then, of course, we have the EMR, and we have these two end ranges that really help drive photosynthesis. So when you think of it, why are plants green? Because they reflect that energy. That's right in the middle of that light spectrum. However, that red and that purple light, those are the ones that have all that energy that the plants will take in and use for photosynthesis. Hopefully we remembered that from the previous slide. I won't spend too much time on this. This is more of just a review. We've looked at photosynthesis lots, but we have to remember the sun's energy comes in, CO2, H2O are also brought into a plant, and then a simple sugar and oxygen is released. And then from past chapters, hopefully remember that, okay, plants die, get covered up, and get covered by a lot of rock, and then it eventually can get compressed into different oil and gas and different resources like coal as well. And this is turning it into a fuel source that we now use today to power our houses. So fossil fuels are everywhere, and they are used for a wide variety of them. Focusing just in on coal, it is so easy to ship coal around the world, and it's so easy to mine that it is one of these easy sources because when it spills, it's not like an oil spill that just goes out and out and out. But if you have a coal spill, it's very easily to be cleaned up, and so it makes it very easy to ship and it's very cheap, meaning it can be used and burned in a variety of places. A lot of coal-fired power plants will use this as a primary source. And when you think of it, if you don't have the proper scrubbing techniques and removing all these sulfur and nitrous dioxide and all these different things that are the issues with combustion reactions, and you just pollute them out, this is going to be leading into acid rain. And we came and talked about this from our chemistry unit. So remember, 70% of Alberta's energy probably comes from burning coal. Numbers might vary here and there, but most of our electricity, most of our energy that we have is from burning coal. Here we can see some predictive statistics of how the coal and production of different oil and gas resources are going to be increasing throughout the years. That total yellow at the top is kind of the whole world, and then you see China and the United States share of that total. So it's a little concerning about how fast they're going up. And I also wanted to show you another picture of just kind of another diagram of how the statistics are broken down. And you can see China is still almost like 50% of this total coal production. So this is what this one is total coal production for 2017. and they measure it in millions of tons of oil equivalent. So they're relating it to how much does it equal to oil versus coal. So they can actually kind of compare numbers. And you see China, US, two of the major ones. Then Australia, India, and Indonesia are also big players, but the biggest ones are China, US. And you can see the rest of the world. So that blue one, like, would even include something like Canada. So we're not even on a big major blip for this coal production. Kind of crazy how much energy a couple of countries are actually producing. So this is the concern that happens is as coal production rises over this last decade and is predicted to continue to rise, people are thinking that it will rise even more because China's going to become more and more industrialized and they're going to be needing more and more energy. And with more and more people, even more energy on top of that. And so this coal uses and this reclamation of it is going to become very, very important because we have to be good stewards of our environment and of the world and make sure that we use it safely and sustainably. Now talking about petroleum, so a little bit kind of a offshoot of just the coal, but petroleum is going to start seeing this huge increase in the 1950s because it has now kind of become our dominant fuel source. One, because automobiles, we love driving around and they do use gasoline and these petroleum products so we can actually drive around. And then with all this, when you think of petroleum and all the byproducts, you get things even like petroleum jelly. So that Vaseline that people put on their lips, this is an oil byproduct, or all the plastics and all the different clothing that we use petroleum products for is incredible. And so this is becoming a huge, huge industry more than just combustion reasons. Another kind of gas that's branched into all of this industry is natural gas. And so this is primarily those smaller chain ones. So if we remember back in our chemistry where we had methanes and ethanes, these are the small gaseous carbon chains that we were naming. And that's what we see here. And we kind of branch them all into this natural gas. They're in a natural gaseous state. So quickly, just about these fossil fuels, to recap a lot of the stuff that we learned from organic chemistry earlier is all this changes that happen within these fossil fuels. So hopefully we can draw back on some of our ideas from chemistry, and we understood that the formation of these fossil fuels required heat and pressure and this long time. So hundreds of millions of years to actually form these. Like I was saying, they are non-renewable. It takes hundreds of millions of years. It can be anywhere from 50 to 300 million years to form. It depends how refined and how clean or how pure these oils want to be. So there is different levels of purity and cleanliness and what is mixed within these different oils and gases, and it depends on time, heat, pressure. And so the world's petroleum production and this refining of it, because like I said, there's different levels of purity, is also increasing. As the world's population gets larger, so does our production and refining of this also increase. And so as of right now, some scientists, many scientists, believe we've used up about half of the whole global storages of all the oil and gas in the world. So now that we've talked about the review of how we're getting all this energy, how do we actually harvest and we're using it, and we're going to actually start putting some of the numbers into the solar energy and how do we actually get tangible energy numbers from all this coal and fossil fuels and everything else. And so it's going to come back to these combustion reactions and the chemical potential energy released that requires O2 or oxygen to occur. We are going to be using something called Hess's law, and this is going to be able to predict the heat of combustion and the energy change in a reaction. And this is going to be the big meat and potatoes part of our lesson, and we're going to be comparing the heat of combustion for the products, and then we're going to be taking it away from the reactants, and we're going to be figuring out the total energy in the combustion reaction. I have a quick little snippet of page 5 in our data booklet. I'll have it more on a screen later, but you'll be using this table and all these numbers to go with it. So quickly, here is an example of a combustion reaction. It's exothermic. We know it. That's why we burn things, is because we're getting energy out of the reaction. Hopefully we remember CH4 is methane, and what we're going to see is the potential energy of the reactants, and then heat is released, H is negative, and so this potential energy of the products is much lower, meaning we've released energy because the potential in the reactants, the potential for this energy is much higher than the potential in the reactants, meaning energy can be released. So we understand chemicals have energy locked up in their bonds, and when this energy release happens in a combustion reaction, we get things like moving a car. In your work booklets, you're going to see this example of 2 moles of octane, and I'm going to go over a simplistic question first, and then we'll try to solve this one later. I also want to remind people, before we jump right into the example, that combustion reactions can take many forms, whether it's in radiant energy, infrared and visible light photons, kinetic energy, heat energy. These things can occur in a multitude of ways. Okay, so let's start with this heat of combustion, and this is the amount of heat released when a substance undergoes combustion. Okay, we understand that. It makes sense. Heat of combustion, and when it's released, when it undergoes combustion. This is where we're going to have to make sense in our heads, and we have to understand that if the products have a lower potential energy than the molecules in the reactants, this means there's a release of energy. That was the graph I showed you a couple slides ago if you wanted to back up the video and think it through. This means that there is a release of energy, and we're calling this exothermic. So the products have a lower potential energy than the molecules of the reactants. So there's more energy in the reactants, less energy now in the products, meaning it was released. Now the opposite is if the products have a higher potential energy than the molecules in the reactants, this means energy was put into this reaction, or energy was absorbed, and we use the term endothermic. That means you needed to put in energy for the products to have a higher potential energy, meaning it took energy in. Something like photosynthesis. You need to put energy into that system, and then they're going to make this big sugar molecule, and this product will have a higher potential energy than the reactants in the start of the reaction. Hopefully those ideas made sense, but now we're going to help explain it mathematically, and this is where we're going to have to practice with this. And so when we kind of make sense of the math, it might even clear it up a little bit, and what do the numbers tell us? So when we see it, don't be surprised. I'm going to break down, and hopefully we see the colors, and we're going to link it all together. So some new symbols for some things, but we should be familiar with most of them. Here we're using this R for this energy of change of the reaction, so that's our total. And all we're doing is going products minus reactants. And if we see this little symbol, if people haven't taken this in math class yet or don't remember it, this little symbol right here is going to be the sum of everything in the products minus the sum of everything in the reactants. Perfect. And then N, as always, is the number of moles in our chemical equation. F is going to be the standard heat of formation, going back to that table I showed you earlier, and we're going to come back to that now. Here we have standard heats of formation of selected compounds. So every example, hopefully every example I'm giving you or anything you're going to be tested on will be on this table, and you'll be able to look it up. The one thing to note is you will not see any elements on this table. Elements are given a value of 0. So you just assume. So O2 is just an element, and it's just given a 0 in kind of combustion reaction. So you don't worry about it. You won't find them on this table. So don't bother looking for elements. And remember that once we start doing practice. Then, also at the bottom, I've blown it up. You can see negative signs denotes exothermic change. Positive signs denotes endothermic change. So that's kind of your reminder of whether reactants or products have more energy. These positives and negatives are going to tell you energy in or energy out. So the steps, pretty easy. We're going to have a balanced equation, which we know how to do. We're going to look up all the heats of formation for the products, all the heats of formations for the reactants, and then just simply go products minus reactants. The one trick is we have to make sure it's balanced because the number of moles matters. So on to a very simplistic. Here I'm going to give a simplified example. I have some made up data, and let's pretend here's my table. And here is compound A, B, C, D. Remember, elements are not included. So I want to call them compound A, compound B, formed together to make compound C and D, whatever the heck they might be. And it takes 2 moles of A, 3 moles of B, and we get 5 moles of C and 1 mole of D. Wonderful. So we label reactants and products, and we're all balanced. We know how to do it. And all we have to do is look up at the table. A is negative 10 kilojoules per mole. However, we have 2 moles of it. So we just times it by 2, and we get a total of negative 20 kilojoules. Pretty straightforward. Do the exact same thing for B, where we have 3 moles, and we look it up on the table right here, and it is now plus 4. So it's a little bit different, but we have plus 12 kilojoules. We add them all together because remember, we are taking the sum of the reactants, and we will take the sum of the products after. Okay, and for a grand total of negative 8 kilojoules. As we're looking, remember, we have to follow the units. We had kilojoules to start, or kilojoules per mole to start, but because we times it by 2 moles, moles cancel and we're left with just kilojoules. Now let's do it for same thing for the product side. Here, 5 moles of C, 1 mole of D, for a grand total of negative 150 kilojoules. Perfect. We already see there's an imbalance. Now we simply go products minus reactants. So 150 kilojoules minus 8 kilojoules, minus negative 8 kilojoules, gives us a grand total of negative 142 kilojoules is released. So remember from that table from before, negative numbers denotes exothermic reactions. This is a negative number, meaning this is an exothermic reaction. Finally, we're back to where our workbook picks up again, and I've kind of explained the basics of Hess's law. Please pause the video if you can and try to look up the heats of formation of this question and see if you can answer it. As a helpful little tool, this was taken right from the textbook. So if you looked up in your textbook, you would see this listed out as well. And it's just broken up the products and reactants just like we did. So we see over here is all the reactants. Over here is all the products, and they outline them in the table. They put products first because we will be going products minus reactants. And so we see CO2, we have 8 moles of them. You go heats of formation of CO2. Water, here you have it, as you'll notice, pay special attention to the signs here, okay? Whether it's liquid or gas, different heats of formation, so be careful with that one. Reactants here, and we have butane, and then oxygen is our element. So I want to remind you, elements are given 0, right? So they have 0 effect on it. So as we calculate it out, remember we have the sum of the products and the sum of the reactants. And so once we total them all up, we have products here at the top. We have our reactants here as the second line, and we get our grand total of products minus reactants. Okay, and we have a negative number. The energy change for this reaction is negative 5,314.6 kilojoules. Hopefully we clued in that we're burning butane. Combustion reactions, the reason we burn them is for energy. So this is an exothermic reaction. It's a combustion reaction. It makes sense that, oh, right, we're giving off energy. So please now take time to work through your workbook, and I'm just going to wrap up the few last little slides of our notes. So first law of thermodynamics, second law of thermodynamics, please review them and make sure that we're understanding how energy is in and out of these systems. And remember that machines are not 100% efficient. Through all these different energy conversions, we're going to be losing energy in different ways. And so we cannot create or destroy energy, just can't happen. Energy is always conserved. However, we're going to be losing it in one form or another. And this is where that second law comes in, is heat transfers always to the surroundings, and it's usually just wasted as heat energy. This is where we come up with our simple percentage formula, where we take our useful output divided by our input times by 100%. It's like our test. What did you get right on the test? Goes on the top. So how many did you get right out of how many was the total test out of? So if you got 40 questions right out of a test of 45, well, you just go 40, your output answers, divided by 45 times by 100%. One example of coal-fired generating stations and how they are efficient or potentially inefficient, or how efficient they can be, is we see here the potential energy stored in coal. But through all these different energy transfers, we have kinetic energy, changing it into high pressure steam. So we burn it and we need to heat up all this water. And then we need to spin the turbines. And then this turbine needs to spin in a generator. And then we transmit it through electricity. However, at each stage, we're going to be losing energy because not 100% of the coal's heat goes into heating the water for steam. So we lose heat. At the same level, when we go into using that steam to spin the turbine, we're going to be losing heat because these are machines. They are going to be grinding, and through friction, they create more heat. And so there is a loss of energy. And the same thing when it's transmitting through these power lines, there is energy being lost, and you guessed it, it's being lost as heat. The longer the power lines, the more heat they give off. It's very small amounts and we insulate. However, there's always losses of heat. So talking about all these fossil fuels and having this heat and making sure we're good stewards of the earth, we're talking about these demands and being sustainable on Earth. Our global energy demands right now are increasing. However, our traditional energy sources are decreasing, like fossil fuels. We're using them up. They are non-renewable. So we need to make sure we're working sustainably while we still can, so we have energy for the future. That's what the sustainability is. It's the ability for us as a population to maintain without loss of essentials. So how will you, as children right now growing up, be able to live for another 50, 70 years and having the same level of energy, or potentially more? And then your children and your children's children. I know it's an old cliche, but we need to be thinking about that. Currently, right now, this is not happening. We do rely on fossil fuels a lot. However, use them now so we can build sustainable development and make electricity for the future while we have the ability to use these fossil fuels, is something that we're hoping to work towards right now. Lots of oil and gas companies are obviously aware of this, and that's their sustainable development. They are trying to develop industry and natural resources that meet the present generation without compromising the future. They understand this is a limited resource, and they are working so that there can be energy and resources for the future as well. There's always this doom and gloom, but they are using the current resources to hopefully give an advantage to later generations. So I will pause it here on sustainability, and we're going to talk about these three types of sustainability, but try to go through the textbook and summarize each three of these different types of sustainability. For the big one, we've heard a lot about ecological sustainability and making sure planet Earth is still around for the future. However, what about societal sustainability? What about economic sustainability? What does it mean to be sustainable in those two regards? So take some time if you've got through these notes and try to figure out how do these three types of sustainability all need to work together.